here. So it's no major announcements. We're just going to kind of continue where we left off from last time. We're going to continue where we left off from last time. Let me open up the chat. I am monitoring the chat. So as questions and inquiries. Hey. Thank you. I know. Thank you. I'm in class right now. She just started. Like, she's been quiet all these hours. Now we start class and she wants to like start warming up her vocal cords. All right. Let me see. Robinson. Okay. All right. So yeah. As you have questions or anything, I'm monitoring the chat, or either feel free to unmute yourself. We're just gonna kind of continue where we left off, exploring polynomial functions. Okay, so today we're gonna finish out this section today. Remember, we don't meet on Wednesdays, so then we'll be back after this on Thursday. Thursday we'll probably go through the homework, and then Friday we'll probably get some practice on factoring, right? Just to make sure that we're comfortable with factoring. Okay. So we want to start the topic with real zeros of polynomial functions. If f is a polynomial function and c is a real number, then the following statements are equivalent, right? So if we say that if c is a zero of f, c is a solution or root of the function, c is an x-intercept of the graph, these four terms are synonymous. We use them interchangeably. So if you ever hear me say any one of these four, they all mean the same thing. Okay. So we're asked to find the zeros of each polynomial. I think we need some space for this one. All right, we're gonna drop that right here. All right, that's good. Let's do it like this. Okay. So let's start with part A, and actually I know we're gonna need a second page. So part A, we have f of x equals this x to the 4 minus 2x cubed minus 3x squared. So if we're going to find the zeros, what we want to do is set it equal to 0 and solve. Now looking at the original, there's a greatest common factor. What do all four have in common? They all have in common, we can factor out an x squared from all the terms. All right, let's bring this down. So then what are we going to be left with? We're going to be left with x squared minus 2x minus 3 equals 0. And then it looks like the next part we can actually go ahead and factor as well. So we're going to say x and x. Because this sign is negative, I know the signs have to be opposite. This tells me that the larger one is negative, right? So we're going to have a positive and a negative. Two numbers that multiply to give us negative 3 and add to give us negative 2. It's just negative 3 and 1. Okay. So at this stage, we're going to invoke what's called the zero factor property. When things multiply to give us 0, basically set each thing to 0 and solve. So we're going to say x squared equals 0, or x plus 1 equals 0, or x minus 3 equals 0. Okay, from the first one, we get, from each one, ultimately we get x equals negative 1, negative 1, 0, and 3. Right? So these are the results that we got there. Okay. And then for B, and we need to check these in the context of the original, but I'm going to go ahead and do B. We get this x cubed minus 2x squared plus x minus 2. Okay, I'll be right back. Take a moment to see if you can go ahead and set it equal to 0 and see can you factor it all the way. I'll be right back. All right. Sorry about that. We're back. Okay. So let's do the same thing here. Let's see if we can factor, set to 0 and factor. All right. So now let's start here. Let's do this. X cubed minus 2x squared plus x minus 2 equals 0. All right. Notice there's no greatest common factor, so we have 4 or more terms. So I'm going to invoke the technique of factor by grouping. If I group the first two together, we can there's a common factor there. They both have x squared. We can factor out an x squared from both of those. And then what's going to be left is look like it's going to be x minus 2. The hint is that we're looking for another x minus 2 on the right-hand side. On the right-hand side, what do they have in common? They both have a 1, so that's the greatest common factor they have, so we're going to factor out a 1. But the whole point is we wanted them to have the common binomial factor. They both have the blue thing. So then we could factor out that blue thing, right? And we'll get this. Okay? And then we're here. Okay. So now that we have two things that multiply to give us 0, we can use what's called the zero factor property. So when two or more things multiply to give us 0, long story short, we set each thing to 0 and solve. So if we set x minus 2 equal to 0, we get x equals 2. And from the second one, if we set it equal to 0, we get non-real solutions, right? We get imaginary results. Okay. All right. Let's see. So we wanna check these results that we got in the context of the original. Okay. So what I'm gonna do, I'm gonna use my graphing calculator to do so. Oops, didn't really want to show all that, but that's okay. This one, right? Okay. Okay. So let's see how to check this in the graphing calculator. So I'm going to go to my y equals, and I'm going to type f in. F was x to the power of 4 minus 2x cubed, 2x to the power of 3, minus 3x squared. And then the next one was x to the power of 3 minus 2x squared plus x minus 2. Okay. So now I just went on to type both of them in, but yeah, so I'm going to quit. So then, now, next to the left of here's the clear button. To the left of the clear button is a button that says VARS. I think it stands for variables. I'm going to click on that. I'm going to go to the right to go to Y variables. I'm going to click on number 1 for function. And I want to call in the first function that I typed in, which is the Y1, right? So what we're saying is that when x, this is like doing f of -1, f of 0, f of 3, right? So when we plug in these values in any of these 4 cases, the output should be 0. Okay. So when x is -1, we get 0. When x is 0, we get our 0. When x is 3, we get our 0. And then for the second one, for that fourth one, I'm going to go back to variables, y variables, number 1. And instead of y1, I want to click on number 2 for y2. And then for that one, we got x was 2. We should still get 0. Right? So we found the zeros. Yeah, we found the zeros of the polynomials. Okay. Okay. Maybe I could do that. Okay. Oh, I need that dolly. Just have to, hopefully I'll remember. I don't even know if it'll fit. Okay. So then we have this theorem called the intermediate value theorem. So let A and B be two numbers such that A is less than B. If f is a polynomial function such that f of A and f of B have opposite signs, then there has to be at least a number c between A and B that's going to produce a 0. That's going to cross the x-axis, right? All right, so let's see this in action. So again, we have some, notice the f of a on the left here is positive. The f of b over here is negative. And so because we're dealing with a polynomial, remember, one of the properties of polynomials is that they're smooth, continuous, unbroken curves. So if the sign goes from positive to negative, that means it has to cross the x-axis somewhere between those points. It's going from negative here to positive here. So it has to cross the x-axis somewhere between. We have smooth, unbroken curves, right? Okay. And it might even, this one is going from positive to negative. It might cross more than once between those 2 points, right? But we should have at least 1, 0 between those 2 points. Show that this function has a real 0 between 1 and negative 2. Well, let's just do it for now. So again, notice that this is a polynomial. All the coefficients are real numbers, and all the exponents are non-negative integer exponents, right? Exponent here is 3. Exponent here is an implied 1. This is x to the power of 0. Okay, so what we're going to do, if we do we're going to evaluate f of 1 and f of 2. If we do f of 1, that's going to be, let's do a negative 2x cubed plus 4x plus 5. And the x in this case is 1. So then this is going to be negative 2 plus 4 plus 5. 9 minus 2 is 7, which is positive. And then we're going to do evaluate f of 2. Again, it's going to be a negative 2x cubed plus 4x plus 5. But the x in this case is 2. Okay. 8 times 2, that's going to be a negative 16 plus 8 plus 5. Negative 8 plus 5 is negative 3. Notice that this result is negative. So because we have a sign change that goes from positive to negative, then we're guaranteed a 0 somewhere between 1 and 2. Okay. Maybe we might have time at the end of class. If we don't do it today, we'll definitely do it on Thursday. Okay. It just depends on if we have time to do it. A polynomial function of degree n with real coefficients has at most n real zeros, right? So whatever the degree is, it has at most that many zeros. Find the number of distinct real zeros of the following polynomial functions of degree 3. Let's add a page. Let me get a copy of this. All right. So we're asked to find, and let's do it like this, view. So find the zeros, all right? So then for part A, we have f of x equals x minus 1 times x plus 2 times x minus 3. Okay, fortunately, this is already factored for us. So if we set it equal to 0 and solve, we would get x equals, let's do negative 2. Yeah, let's just keep it in the same order. So x equals 1, negative 2, and 3. Notice that the power on each of these linear factors is 1. So the multiplicity of all of these is 1. So the graph would cross the x-axis at each of these x-intercepts, right? Okay, so this one has 3 distinct zeros. These are the 3 distinct zeros. Okay, so then part B, if we have g of x equals, we have this x plus 1 times x squared plus 1. Again, if we set it equal to 0, one of the zeros is going to be negative 1. The other one, if we set it equal to 0 and solve, we get non-real solutions. So this one has one distinct zero, real zero, which is the negative 1. So then for part C, we have x minus 3 squared times x plus 1. Again, if we set each one to 0 and solve, we'll get x equals 3 and negative 1. But because the degree has a degree 2, so this one we have 2 distinct real zeros, and we say that the 0 of x equals 3 has a multiplicity, has an even multiplicity of 2. Right, so that means it's going to bounce off the graph. If it has an odd multiplicity, it's going to cross the x-axis. If it has an even multiplicity, it's going to bounce off of the x-axis. It's going to touch and bounce. Okay.
I have a question.
Go ahead.
For B and C, you're taking what's in the parentheses and you're setting them equal to 0?
Yep.
For both B and C?
A, B, and C, all of them. That's what I'm doing. Yep. Set each one equal to 0 and solve. Okay. So then if we go to the view, you can see it here. So we set each factor equal to 0, and that's how we're doing these. We're going to look at B and C, the same thing. So then the multiplicity of a 0, we kind of mentioned this already, but let's go over it officially. If C is the 0 of a polynomial function, and the corresponding factor occurs exactly m times when when f of x is factored, then C is called a 0 of multiplicity m. All right, so for instance, if the multiplicity is odd, it's going to cross the x-axis. If the multiplicity is even, it's going to bounce, it's going to touch or bounce, but does not cross the x-axis. Right? So like for instance, if we were to look at the graph of part C, when x is 3, it's going to bounce off the graph at x equals 3, but it'll cross when x is equal to negative 1. So this is the multiplicity. This is the multiplicity. Okay. So when we have an odd multiplicity, it's going to cross the x-axis at the value of c. It's going to cross. When it has an even multiplicity, it's going to touch and not cross. It's going to bounce off the x-axis. It's going to bounce. Find the zeros of the polynomial function and give the multiplicity. So again, fortunately, this is already in factored form for us. So like basically we set each one to 0 and solve. So the zeros that we get 0, negative 1, and 2 because it's already factored. And then the multiplicity of 0 is going to be 2 because the exponent is 2. The multiplicity of the negative 1 is going to be 1. Multiplicity of the 2 is also going to be 1. So what that means is that if we were to look at this graph, when it crosses on the x-axis, when x is 0, it's going to bounce off the x-axis. For x equals to negative 1 and 2, it's going to cross the x-axis of both of those x-intercepts. Okay? So then turning points, we have local or relative maxima. Is f value that's higher than any nearby point on the graph. And a local minima is going to be lower than any nearby point on the graph. So like the relative max and min, it's like the relative max is like the peak of a mountain, and the relative minimum is like the bottom of a valley, in a pictorial sense, in a graphical sense, right? That's what's going on there. And the graph changes from increasing to decreasing or vice versa at these turning points. So for instance, here's some examples of turning points. So the graph has 2 turning points. One is at negative 112 and the other is at 2, negative 15. Notice that the graph goes from increasing to decreasing, so we have a relative max. And then over here, the graph goes from decreasing to increasing, so we have a relative minimum. Okay, and we always read the graph from the left to the right for these discussions. Okay. If f of x is a polynomial of degree n, then the graph of f has at most n minus 1 turning points. So, given the degree of a polynomial, we have at most n zeros, and we have at most n minus 1 turning points. Right? So we're actually use a graphing calculator in this window to find the number of turning points of the graph of each of these. Okay. So go back to my calculator. Okay. So then I'm going to type in each of these. I'm going to go to my y equals. The first one is x to the power of 4 minus 7x squared minus 18. The next is x to the power of 3 plus x squared minus 12x. And the last one is x to the power of 3 minus 3x squared plus 3x minus 1. The x-axis to do that window, so I'm going to go to window. I think the x scale is fine, but on the y-axis, we need to go from negative 30 to 30, and I'm going to go in steps of 3. Okay. So if we hit graph, oh, wait. Oh, can I stop it? No. You're not going to let me. Okay, I think I got to let it finish graphing. I meant to suppress the other one so we didn't see them all at the same time. Okay. So it makes an interesting picture, though. Let me go to y equals. Let me suppress these other two so we can focus on one. So if we look at the first one, find the number of turning points. So if we only see the first one, we have we have 3 turning points for that first one. 3 turning points. 2 local minima and 1 local maximum. Okay. So then, for the second one, if I hit graph, 1, 2. 2 turning points. 1 local maximum, 1 local minimum. And then the third one, going to suppress the second one and activate that one. Let's go to graph. So for it to be a turning point, it has to go from increasing to decreasing or vice versa. This one never went decreasing, so there are 0 turning points here. Okay. All right. All right, so we actually sketched the graph here. Let me add a page. Copy, paste. Add a page. And let me get a copy of this. Uh-oh. Oh, okay. So, okay, maybe we can keep going. My battery's hanging on for dear life. It's plugged in, but it needs to be plugged in and like left alone for the. I mean, I think we can make it to the end of class. I'm just gonna kind of keep going until we can't go any further. Get rid of this. We just need that. Come on. All right, so we actually sketch the graph of this polynomial. Okay. We're gonna drop this right here. All right, so I'm gonna try to touch on as many we've talked about a lot of different like concepts, right? So this is where the information overload kind of kicks in. So you just have to kind of like brace yourself, do your best, forget the rest, don't stress, and be blessed. Let's go to view seamless. Right? So we're actually sketch the graph. Okay, so one of the first things that we can talk about is the leading term test. This tells us about the long-term behavior of the polynomial. So if we look at the leading term, notice that the leading coefficient is negative. The leading coefficient is going to be -1, which is less than 0, right? So that tells us that the graph falls to the right. It's going to go down to the right. The degree of the polynomial is 3, which is odd. So that means the other side does the opposite. So it's going to rise to the left. I'm going to go up to the left, right? Okay. Let's do the Descartes rule of signs really quickly. Descartes rule of signs. Okay. So the way Descartes rule of signs goes, so for instance, if we look at the original, f of x equals -x cubed minus 4x squared plus 4x plus 16. So if we count the number of sign changes, we have one sign change, right? So what this means is that there's one possible positive 0. All right, so if we find a positive 0, then we know it's not going to be any more positives. Okay. So then let's test for the negative zeros. We're going to do f of negative x. Okay. Let me see. That's going to be, so that's going to become a positive x to the 4. No, x to the 3. That's going to stay the same. That's going to become this. This is. So now if we count the number of sign changes, we have 1, 2. Right? So what this means is that we have either 2 or 0 possible negative zeros. Okay. So then let's go ahead and let's do our rational zero test. So what we're saying is that if this function has any rational zeros, it's going to be somewhere in the following list. If we do our p over q, where p are the factors of the constant term, in this case the constant term being 16, the factors of 16 are going to be plus or minus 1, 2, 4, 8, and 16. So if this polynomial has any rational zeros, it's going to be somewhere in this list. One other thing I want to mention is a test on symmetry, since we've already kind of done it already. Symmetry, and let me show you what I mean. We want to do a test for symmetry. So the test for symmetry, if we did f of negative x, right? I think we did this one already, so we did it right here. I'm just going to copy this and paste it here. So now, if we do f of negative x, we get this result. Notice this is not equal to the original, and if we try to factor out a negative from everything, we still can't get a form of the original. So there's no symmetry. There's no symmetry. Okay. So now let's go through. For some reason, I want to start with 2, right? I kind of want to do a test. I want to see if there's a bound, but let's start with the number 2. I just want to start with 2. So then we're testing Here, let's do this. Well, this is fine. So the coefficients are going to be, I need the coefficients from the original. This -1, -4, 4, and 16. Let's cut. What's the time? We're going to paste. So let's see what happens when we test this number. We're doing synthetic division. So with this synthetic division, whenever we go vertical, we add. So this is going to be a -1. This one, the first one just comes down. And then on the diagonal, we multiply by the 2 in this case. So then 2 times -1 is -2. -2 plus 4 is -6. This is going to be -12. That's going to be -8. It's going to be a -16. And it adds up to 0. So what that means is that 2 is one of our zeros. Since we started with a degree, where is it? We started with the degree 3 polynomial. At this stage, is now this depressed equation is now a degree 2. X squared minus 6x, right? So let's list out what we have so far. If 2 is our 0, that means we have, so this the original f of x is going to be equal to, and let me actually get a copy of the original because I don't want to have to keep scrolling back and forth. Let's copy. Okay, let me give myself some more space. So now f of x can be expressed as, so x minus 2, because 2 is a 0 we just found. And then what's left over is going to be, it looks like we have a -x squared minus 6x minus 8, right? So we should be able to just factor it from here. We can start by factoring out a negative from all the terms, and we'll get negative times x minus 2. We're going to have x squared plus 6x plus 8. So then it looks like we can factor that even further. This factors into something of this form. X and x. This tells us the signs are the same. This tells us the larger is positive. So we're going to say plus and plus. Two numbers that multiply to give us 8 and add to give us 6 are 4 and 2. So then what this is basically telling us, it tells us that the x-intercepts, so we're going to do it. We kind of did it. We didn't develop the idea all the way, but number 5 is we can do upper and lower bounds or a test on the bounds, but we didn't finish it because we found a 0. Once we found a 0, then we just took it and ran with it. So then we can do the intercepts. Again, and we'll make that number 6. We found we already found the x-intercept. So we got that the x-intercepts are let's see, we got a -2 to, let's kind of keep the order. So from the first factor, we get 2, then we get -2 and -4. So if we can find the x-intercepts, we can also find the y-intercept. So the y-intercept, if we go back to the original and set x equal to 0, this goes to 0, this goes to 0, this goes to 0. Only thing that's left is the 16. Okay, so the y-intercept is going to be 16. Okay. Also, notice that the multiplicity, let's talk about the multiplicity. So when x is 2, all the multiplicities are 1, so that means it's going to cross the x-axis on each of these intercepts. And then the 7th thing I would do is just a few additional points. Okay. So let's put all this together. So I'm going to do my y-axis. Positive x is in this direction. Let's move this. Let's just a little bit more centered. Let's crooked. Okay. Let's move it. The first step is a little weird. Okay. Let's go back. So then the first thing that we found, we said what it falls to the right and rises to the left, right? So we're anticipating it to fall to the right. So it should be going down in this direction and rise to the left, up in this direction. Let me see. Descartes rule of signs, it tells us the possible number of positive and negative zeros. So we said one positive and two negatives, I think. Did we finish? Oh, yeah, a little bit. One positive and two negatives, okay. Rational zero test. We said there was no symmetry. In trying to do the bounds, we found the zero. So once we found the zero, we went on to find the other ones using factoring. And then, so we got our x-intercepts, y-intercept. Okay, so let's graph these x-intercepts. So let's, need to put some tick marks. Let me see. So then, let me move you out of the way. I just want to get a copy of you guys. Is this going to be enough? Okay, I might just change my scale. Okay, so here's the origin. On the x-axis, I'm just going to go 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. These are supposed to be negative. I need to go to 20 on the y-axis, so I'm going to go by fours. Let's see. 4, 8, 12, 16, and 20 would be here. 4, 8, 12, 16, and 20. These are all negative. Okay. So let's plot the x-intercepts. So the x-intercepts that we got negative 2. We got 2, 2, negative 2, and negative 4. Right? So, and I'm going to move these arrows. So again, we said that it crosses for each of these, so we're anticipating it crossing there. It should cross here. And we still have this notion of falls to the right, rises to the left. Okay, so this is what we're anticipating. We got a y-intercept of 16 that we can plot. So that's going to be about here. And then a few additional points. We want to find a few additional points between and beyond our x-intercepts, right? So what I'm going to do, here to my y equals. Oh, okay, there we go. Reload and refresh. Let's see, I'm going to type in the original. We get this negative x to the power of 3 minus 4x squared plus 4x plus 16. Okay. Now, we're going to quit. Now, when x is, let's do -5. I'm going to go to variables. When x is -5, what answer do we get? We get 21, right? So we get this -5 and 21. We can, let's go like this. Paper, -5. So it's about here. Right? This is -5, 21. All right. I'm just going to choose a number halfway between the -4 and -2. So when x is -3. So when x is -3, we get -5. So that's 4, that's 6. So -5 is about here. This is -3, -5. Okay. We already did when x was 0. So I'm going to do when x is 3. Just select something to the right of that. And so when x is 3, we get a -35. So it goes off the chart. So then we can connect these notions with a smooth, continuous, unbroken curve. So we're going to get something like this. And we're anticipating a graph similar to this. Okay, and let's go to window and let's match their window with ours, right? So let's do like, we can do -7 up to 7, and steps of 1 is fine. Let's go -22 up to 22, and we went in steps of 4. If we hit graph, we should get a similar, if not the same, image. Okay. Well, let's see. So let's go to view, single page. So again, so notice the degree was 3. So as our leading coefficient was negative, the negative leading coefficient tells us it goes down to the right. Because the degree is odd, the other side does the opposite. So down to the right, up to the left. So then we set it to 0 and solved. So we factored it. Each 0 had a multiplicity of 1, so it's going to cross the x-axis of each of those multiplicities. So notice it still falls to the right, rises to the left, and it crosses the x-axis at each one. So then in the factored form, we found our x-intercept. So if we can find our x-intercept, we can also find the y-intercept. So for the y-intercept, we said x is 0, and we got 16. We did a test for symmetry. There was no symmetry because we couldn't get back to some manipulation of the original, so there's no symmetry. And this was choosing a few extra test points, right? Between and beyond our x-intercepts, right? I think they chose the same test points we did. Okay. So then we connected the points with a smooth, continuous, unbroken curve, and we got an image like this. Okay, I want to say I think we have one more example, and then after that example, we're actually going to have to... I can glance... go ahead and make use of the Ask My Instructor. I know there was a request on number 12 for 2.2, but I mean, honestly, that's what we're going to do on Thursday when we come back. I'll start with that one if you haven't figured it out by then, because I kind of do need to kind of go today, and we're almost out of time. We have just enough time for one more example, which is this one. And let me give myself some space. I need to add a page. Okay. So it says, express the volume. This was a little intense. Express the volume of the wine barrel as a function of x. We're given that the height divided by the diameter, so the height of the barrel divided by the diameter, ultimately is going to be equal to z over r equals the square root of 2, right? So we want to use this image, and we want to express the volume as a function of x. Okay. So let me go to view. Let me go to seamless. And let's do paper. Let's get some graphic. Okay. So now, notice the basic shape is a cylinder. the base is a circle, and then it's a cylindrical prism. It's a soft deadline for all of our assignments is Saturday by midnight. It's not a hard deadline though. Just on a weekly basis, we just want to be doing our best to complete about 25 topics per week. If we're having trouble, any kind of trouble with Alex, you want to reach out to Dr. Tawana Lamar, and she'll have all the details that you would need to kind of make sure that's working operational, working properly. Okay. Let me kind of go ahead and finish this one. Yeah, hopefully that answered the question. Let me see. So we want the volume, right? So the basic shapes here for a volume, for the volume of a cylinder, in a general sense, for something like this, it's going to be the base times the height, right? The area of the base times the height. So in a general sense, the volume of a cylinder is going to be the area of the circle times the height of the cylinder, right? So it's basically the area of the circle times the height. So let's see if we can find the area of the base, the circular base. So the area of the base, the circle, is going to be, in general, it's going to be pi r squared, right? So we can just leave that as is for right now. That's the area. That's the formula for area of the circle. The height of the barrel in this case is going to be 2z. So if we're still kind of working on this volume formula, if we plug in what we have, area is going to be pi r squared. The height is going to be 2z. Okay. Let me see. We were given some more information. We were also given that z over r is equal to the square root of 2. Okay. All right. Okay. So if we solve for z from here, we'll get this. This implies that what? Z equals r times the square root of 2, right? So then now we can express the volume is going to be pi r squared times 2z, but z is going to be r times the square root of 2. Let me see if I can condense some of this at this stage. This is going to be pi, associative property of multiplication is going to be r cubed times 2 root 2. This is fine. And I'm going to write it, I'm just going to write it a little bit differently. I'm going to say 2 pi r cubed times the square root of 2. Okay, I'm going to leave it like that. I just reorganized it. And this is an expression. This is the volume in terms of r. So now can we get r in terms of x so that we can simplify it? I mean, we can substitute it back in. Okay. So now it looks like we make a right triangle. So it looks like z squared plus 2r squared equals x squared. It looks like z squared plus 2r squared equals x squared. That's Pythagorean theorem. Okay. Let me add a page. Okay. Let me see. I'm trying to keep it as simple as possible. Okay, we have z in terms of r. So let's go ahead and make that substitution. So I'm just going to go ahead and simplify. So it's going to give us 2r squared plus 2r squared equals x squared. Okay. Did I do that right? Oh, no, I didn't. I found it. Oh, something's not right. This is supposed to be 2r squared like this. So then what happens when we account for that, that 2 actually becomes 4. That's better. So then 2 plus 4 gives us 6r squared equals x squared. Okay. So now it looks like we can get r in terms of x. So if we solve for r, we're going to get r squared equals x squared over 6. Take the square root. Normally when we take square root, we do plus or minus. but a negative radius doesn't make sense in the context here, so we're only going to take the plus here. And ultimately, normally when you do the square root of x squared, you do absolute value, but we're just going to do x over the square root of 6. Because I think that's what the text does. So then if this is r, we're almost there. So then our volume is going to be 2 pi, I'm just getting a copy right now, r cubed times the square root of 2, right? So let's substitute this in for r. And so now, if we want the volume in terms of x, that's going to be 2 pi. What's r? R is going to be x over the square root of 2 cubed times the square root of 2. Okay. Let me see if I can simplify this down some. If we have root 2 times root 2 times root 2, so let me expand everything out, right? So we're gonna have this 2 times pi times, I know, you're on your way out. 2 times pi times the square root of 2, and we still have this x cubed over here to the side, right? That's on top. On bottom, we have, basically we have like root 2 times root 2. I'm writing it this way so hopefully you can see it a little bit better. Okay. So these two, root 2 times root 2 is going to be the square root of 4. Square root of 4 is going to be 2, right? So this should cancel this. Did I miss something? Take the square root. Oh, wait a minute. Yeah, I found my error. Doggone it. Right here, we take the square root. That's going to be x over 6. I don't know why I put 2. This is a 6 here. I think that's fine. So then what happens is that makes this a 6. Okay. And then what happens next is, let's undo that and let's get rid of this stuff down here. So then when we take it to the power of 3, it becomes root 6. I'm going to go ahead and kind of jump to one of the conclusions. It's going to be root 36 times the square root of 6, because it's basically root 6, root 6, root 6. So then you can see that there. Okay. So I think we caught a mistake. So then now, that's going to be 2 divided by 6. So then, long story short, this is gone. This is going to turn into a 3. Okay, so I'm going to do 2 more steps. We get this pi times the square root of 2 over 3 root 6. And then all of that, whatever that number is, times x cubed. I'm just going to crunch that number because I know that's what the text does. I got it down as far as I could. I mean, I can go a little bit further, but we're almost out of time. And I kind of need to get going. But I'm going to go ahead and crunch that number and confirm that I get the same result. So I'm going to quit, clear. So what I'm going to do, I'm going to say parentheses. I'm going to do pi times the square root of 2. Close off the top. I'm going to say divided by the bottom is 3 times the square root of 6. Close off the bottom. You should get some decimal. I hope that's the same decimal. Let me see. So then we get this 0. I'm going to do approximately 605 x cubed. Right? Okay. So all I did, I simplified the expression down as far as I could, and then I just went on and crunched the number to find that number. Okay, let me just clean it up just a little bit. This is supposed to be the approximate symbol. And then let's compare it to what the results that the notes got. I'm just going to kind of jump to the end. 0.605 x cubed. Yeah, 605 x cubed, right? What happened to their root 2? Oh, you can pass it. Okay, so they passed the root 2 over root 6. You can pass it into the same radical. It becomes 2 over 6, and it boils down to just the root 3. That's fine. Long story short, we still get the same result. it's a little, that was a little bit intense. It was not that smooth with my earlier group because I didn't. I typically these notes I don't look them in advance. I mean, I just do them off the cuff. Like for college algebra, a lot of these classes I do them off the cuff because I kind of want you guys to get a sense of how to think through some of this stuff. Um, yeah. Anyway, so I know there was a request for number 12. I'm actually going to end class here. We're at our usual ending time, and go ahead and make use of the Ask My Instructor. Send it to me and Ask My Instructor. If I don't respond by Thursday, we'll just let that be the first one that we do on Thursday. Okay. All right, guys. You guys have been awesome. Enjoy the rest of your day, and I'll see you all in 2 days. Take care.